The objective of this video is to introduce inductor and capacitor selection and rating in power converters. We will do this by again considering the single-pole double-throw converter. We have previously discussed the need to add voltage and current stiffeners to the converter in the form of capacitors and inductors. In the circuit drawn here, we have added two capacitors to provide voltage stiffness. One is on the input side of the single-pole double-throw switch to stiffen our power source's voltage. This is needed due to the internal impedance. The second capacitor is added in parallel with the load to stiffen the output voltage. Finally, an inductor is placed in series with the pole to provide current stiffness. This video is going to discuss the procedure for determining the value of these capacitors and inductors. In most of our analysis so far, we have considered our voltage and currents to be perfectly stiff. In this video, we will acknowledge that we have ripple in addition to these DC quantities. We will label this as delta I and delta V. We will begin our analysis by recalling the fundamental property of switch mode power electronics, which is that they repeat over a certain interval called Ts, corresponding to the switching interval. So these converters have a switching frequency, Fs, which is equal to 1 over Ts, and over this switching frequency, the pole of the converter is connected to each throw. In steady state, this is completely repeatable. That is to say that conditions repeat every Ts seconds in steady state. And these conditions are the various currents and voltages in our circuit. The average value of these quantities is determined by our design specification. When we go to design a single-pole double-throw converter, we're going to know what the output power is required to be, what the output voltage and current should be, what the input voltage should be, and so on. However, within the switching interval, that is, over the period of 0 to Ts seconds, the instantaneous values, the instantaneous voltage and currents, will deviate from these average values. And this deviation is what we are capturing with the delta labels. So all of these quantities are referred to as ripple. Ripple current, ripple voltage, ripple pole current, ripple inductor current, ripple output voltage. And so we will have a design spec that will also place limits on the maximum value of these ripple voltages, or rather the maximum ripple observed. It's the designer's responsibility to take these ripple values into consideration in order to calculate the required value of L and C for the voltage and current stiffeners that are to be used. And the designer does this by inverting the problem, that is, going from the desired output behavior and calculating backwards to find the parameters that are needed. So this is done using the differential equations for voltage across an inductor and current into a capacitor. And here we're noting our capacitor current as IC, whereas our inductor current is simply the pole current. Okay, let's now talk through a couple simple exercises. The first exercise is to determine the average value of the inductor voltage. This value should be averaged over the switching interval. So take a moment now and contemplate what is the average inductor voltage when taken over a switching interval. Press the pause button, and when you're ready to resume, press play. Alright, so we can intuitively make an answer to this by looking at the differential equation for the voltage across the inductor. So we know that VL is equal to L di dt, and we know that we have an average inductor current value. That is, that the current through our inductor has a DC component as well as a ripple component. And if it has a DC component, that means that the average value of our inductor current must be constant when taken over a switching interval, which means that there must be no average voltage across it. So if we want di dt to be 0 over a switching interval, VL needs to be 0 over that interval. And we can perform the integral to verify this. And in this integral, we say that we depend on the difference between IL at time Ts and IL at time 0. Well, in the very beginning of our analysis, we stated that these quantities repeat every Ts seconds, which means that IL at Ts is in fact equal to IL at time 0, and therefore we find that we have 0 volts across our inductor. Let's now consider a second exercise, and this will be to determine the average current into our capacitor. Press the pause button and press play when you are ready to resume. So we can similarly calculate the average current, and we find that it has to be 0 amps, because again, the voltage across our capacitor at time 0 must be equal to the voltage across our capacitor at time Ts. Let's now proceed and develop sizing expressions for our inductor. And we'll do this by, again, considering our single-pole double-throw switch connected with an inductor. But this time, we're going to simplify every other component as being stiff voltage sources. So this is a reoccurring theme in this class, that any component which we don't care about a detailed model of, any component that we can possibly simplify, we simplify. So in this circuit, we've simplified our throw voltage and our output voltage to be equivalent DC sources that are infinitely stiff. We do this so that we can study the inductor behavior without the complexities of the rest of the circuit. This allows us to avoid having to solve a second-order differential equation, and we can just stick to a simple analysis toolbox which provides us sufficiently accurate results. So in this case, let's consider that we have a design spec which is going to determine our throw voltage, our output voltage, as well as our switching frequency, our average output power, which we can use to calculate our output current, and finally a constraint on the maximum allowable ripple current through our inductor. The task at hand is now to calculate the value of inductance in order to achieve this ripple current, given the rest of the design spec. And to help us illustrate this, let's consider that our throw voltage is at 48 volts and our output voltage is specified as 12 volts. Let's now draw the waveforms. And we'll specify a couple time intervals. Let's make the calculation of what our duty ratio is for our top throw state. So we can calculate the duty ratio by observing what the average pole voltage should be. The average pole voltage is the same as the output voltage, and we use our relation that we derived previously, which is the duty ratio should be the ratio of the pole voltage to the throw voltage. And so to add some intuitive physical insight here, we're trying to calculate the pole voltage observed at this location, the average of that, with respect to our throw voltage. And so we know that the average of this has to be our output voltage, and if we connect the pole to the top throw 25% of the time, and to the bottom throw the other 75% of the time, we will in fact observe an average of 12 volts on the output. There will be a large ripple, but there will be an average of 12 volts. So we can sketch these voltage waveforms on the top in our graph, and we'll label some time intervals based on this duty ratio as Ts by 4. And let's start by sketching the pole voltage. Our pole is either in the top state, at which point it's equal to throw voltage of 48 volts. And then as soon as it reaches Ts by 4, it goes to the bottom state where it's connected down to the bottom throw, and it's at 0 volts, where it remains until the end of the switching interval, at which point everything repeats. On top of this, we can sketch our output voltage as just a constant DC line, because we've modeled it as a DC voltage source. Let's now sketch our inductor voltage VL. And we can notice that VL is going to be equal to VP minus Vout. So we'll start at 48 volts minus 12 volts, and then we're going to decrease down to a negative 12 volts. And this will repeat. Okay, so let's finally sketch our current waveform. And to help us, you can recall that dIL dt is equal to VL by L. And we'll also recall that we're going to return to the same points periodically. So at time 0 and at time Ts, we will have the same current value. Now at time Ts by 4, we can see that our current is going to have increased because we've applied a positive voltage across our inductor. And since this voltage is constant, we will have a straight line. So our inductor will have an average component, which is the average output voltage spec. And we'll label our ripple component as the extent of the positive inductor voltage, the peak of the inductor voltage, minus the minimum of the inductor voltage. And our task at hand is to calculate IL and relate that to the inductance of our inductor. So we can go back to our differential equation and we can solve it for IL over either of these windows. So we could pick this window, or we can pick this window, whichever is most convenient for us. In this case, we're just going to pick the top window. And if we evaluate this integral, we get the following expression, where this first term is the volt seconds applied to our inductor over the interval, or it's in units of the change in flux linkage. And when you multiply that by 1 over L, you get your delta IL quantity, the change in ripple current, or the change in current. So we can solve this as delta IL, and finally we can obtain an expression for our inductor. So we can now use this expression to calculate the value of our inductor for some example cases. So taking into account our previous design spec of 48 volts to 12 volts, let's add in there that we're switching at 1 megahertz and that we want to have a ripple current equal to 10% of our average load current. So we can use our power out expression to calculate what our average load current should be, which requires us to specify the output power. And let's specify that as 120 watts. And we find 10 amps for our load current and our average inductor current. This means that we need to have a ripple current within 1 amp. If we use that in our expression for L, we find that we require a 9 microhenry inductor. Now notice that the value of our inductance is proportional to 1 over our switching frequency and 1 over our ripple current. So suppose that instead of switching at 1 megahertz, we were only switching this at 100 kilohertz. We would require an inductor of 90 microhenries. So by decreasing our switching frequency by an order of magnitude, we'd increase the required inductance value by an order of magnitude. And we'll talk about the design of inductors later, but it's fairly intuitive to see that as we increase our inductor value, we're going to also increase the physical size of our inductor. We're going to increase the number of turns that are required to be on our inductor, which increases both the size and the cost. So in conclusion, we can note that our inductance is proportional to 1 over Fs and 1 over delta IL. So this means that as we tighten our specification on the ripple current, we're going to require larger and larger inductors. Contrarily, as we increase our switching frequency or we loosen our specification on the ripple current, we can get by with smaller and smaller inductors. And that is the reason that power electronics is consistently pushing towards higher and higher switching frequencies. So when we go to pick out an inductor, our ripple current specification and our switching frequency specification determine our value of inductance. Meanwhile, our RMS current and our switching frequency determine our inductor rating. And this is related to losses. The RMS current is going to cause copper losses within our inductor, and the switching frequency is going to cause both copper and core losses within our inductor. And we'll talk about this a little bit more later, but as we increase both the RMS current and our switching frequency, we have to make design changes in order to have a suitable inductor. Finally, let's discuss capacitor sizing. We previously discussed capacitor sizing in our unit on the full wave rectifier, so we'll keep this brief. So considering the output of our single pole double throw converter, we can model it as having a certain current waveform impressed upon it as the output of our inductor, and the capacitor that we are sizing, and then an output current source. So now we're modeling our load as an output current source. And we'll develop sizing expressions similar to the inductor by solving the differential equation for the capacitor. Let's begin by sketching waveforms. And we'll bring over our inductor waveform from our previous example. And next we'll sketch the current flowing into our capacitor, IC. So IC is going to be equal to our inductor current minus our load current, which is again going to repeat at the same intervals that we previously commented on. And we can use this expression to approximate our capacitor voltage. Now we do this by solving the differential equation for the capacitor. And noting that the average of our capacitor voltage is actually our output voltage, we can start by observing that initially the current into our capacitor is negative, which means that our voltage has to discharge. However, about halfway through this interval, the current through our capacitor starts to increase, so our capacitor begins to charge. And I'm going to approximate these with straight lines, but you can see from the differential equation that this will actually be a more arcing contour. However, for our purposes of just trying to calculate the ripple voltage, we can consider this to be a set of straight lines. The appearance of this waveform does not much matter for calculating the ripple voltage. What matters is the maximum deviation, the maximum peak to peak. And we're going to calculate this by again integrating the area within our current waveform. So we can say that the capacitance that's required is dependent on the current into our capacitor over our voltage ripple specification, and the integral of the current into our capacitor is representative of the change of charge within our capacitor, which is again going to be equal to proportional to 1 over the switching frequency and 1 over the ripple specification. So the change of the total amount of change of charge is the integral underneath this curve up here, which is also the integral underneath the second area. And you pick whichever area is most convenient for you. So similar to an inductor, the ripple voltage and switching frequency determine the value of capacitance, and our voltage and RMS current through a capacitor determine its ratings. Before we wrap up, I want to point out that for developing both our inductor and capacitor sizing theory, we've assumed a certain waveform. In the case of the inductor, we assumed a square voltage waveform, and in the case of the capacitor, we assumed a triangular capacitor current. These waveforms were meant to actually be general. You can repeat this analysis with any type of waveform to determine the required value of inductor and capacitor to meet your voltage and current ripple requirements. In conclusion, this video has developed the theory to calculate the required inductance and capacitance in order to meet the design specification for current ripple and voltage ripple in a single pole double throw converter.